Hello, folks. Welcome to Rational Science, the only site on the internet that does physics. Everybody else does mathematics. Good math sometimes, terrible explanations. Mathematics, bunch of movements of concepts. Well, I came out of one of these deaths in the family. One of my sister-in-laws died, and so we're a little down because of that. But the show must go on. So let's get started with subject matter today. One person asked the following. He says, Bill, do you have any videos explaining what object light must be? Light exists, so it must have shape. I'm here wondering, what's its shape, more or less? What is the shape of light itself? The rope? And it is a valid question, for hundreds of years. In fact, I think forever, there's been no other alternative other than particles. A series of particles. That's what everybody always thought that light is, that it's mediated by a series of particles. That's the way it's always been treated. In the 17th century, we had, for the first time, Robert Hooke. He came up and suggested that light could be some sort of wave because he saw it through the microscope, one of these old microscopes of those days, and he saw some fringes there, and so he figured out that maybe, just maybe, light moves in wave patterns. On the other hand, his nemesis, Isaac Newton, he believed that light always travels in a straight line. So it was the waves versus the straight line. But they all believed in the ether and mediated with the ether. And the ether was a bunch of particles. And they thought that that's what light was. And to this day, nothing has changed. They always simulate light as a series of particles. Okay? Row of particles traveling all what they call it in a straight line, meaning rectilinearly. Is that what light is? A bunch of particles, photons, little round balls, I guess, traveling rectilinearly, one right after another, in a straight line, as they say. Well, it's very hard to believe that because, the sun twirls. Every atom in there vibrates and moves around, also spins, as they say. And so, the atom creates light. It sends the first photon, and then it immediately moves, rotates, spins. Sends another one, spins, sends another one, spins, and sends in between. That series of photons can never travel in a straight line. It can only travel in curved lines. It's like a water sprinkler. The first drop goes here, the next one goes right behind it to the side, the other one to the side, the other one to the side, and it describes a curve in space. And so if light were mediated by a series of particles, you would have curved light. We all see it in curves, okay? So no, light cannot be mediated by so-called photons, and particles cannot travel. A series of particles coming out of a source that's moving cannot travel ever. Impossible to travel in a straight line. Then the other issue is, what are the particles somehow connected to each other? So one is pulling on the other in a straight line. Is that how light works? Are they all connected? And so these are valid questions for the structure, the architecture of whatever mediates light. So he asked, what is the mediator of light, essentially? Okay, and so here's what the establishment proposes. They propose that light is some sort of wave. This comes primarily from Maxwell and other researchers of the 19th century who eventually figured out that light is some sort of wave, and they said, well, it's a transverse wave. It's a pair of fields, electric and magnetic fields. Names are irrelevant, but they're fields traveling at 90 degrees to each other. That's more or less how they visualize it. And here's the picture of it. I think you've seen it before. You see up on the top the wave, and at the bottom what we propose. And let's go through this, okay? Let me remove this. So let's go through this, find out what it's all about, okay? So here we have the transverse wave, okay? And what are you staring at? Well, you're staring at a bunch of vectors. That's what you're staring at. The electromagnetic wave that they use out there is so-called transverse, meaning that it travels perpendicular to the motion of those arrows. Arrows go up and down, and a wave travels forward towards your right. And that's known as a transverse wave. As you can see, this is also a two-dimensional wave. That's the notion that we have in front of us. That's what they're illustrating, okay? And so what's the problem? The problem is those arrows are not engine arrows, solid arrows that kill people. Those arrows are actually vectors. Okay, it's known as magnetic and electric field, and what they are made of are these vectors. Okay, here you see them. Okay, those are the vectors that make them. Okay, and so you have the electric field traveling at 90 degrees to the magnetic field, and both of them travel, and the whole wave travels forward. Okay, but each of those fields, which is a mathematical concept actually, is made out of vectors, which is another mathematical concept. Vector only has magnitude and direction. Okay, so when you look at this, what you're looking at, or what you're staring at, is not a physical object. What you're staring at is a mathematical concept which they put in motion. Okay, and so this so-called thing goes one way towards the right in this example. Okay, so it's moving towards the right, and it's made out of vectors, and the vectors make up the magnetic and electric fields. So we have a problem because this is not a physical object. You cannot say that a wave is a mediator for light. Okay. And it turns out that the wave itself is made out of particles. Okay, so we have these waves, and they're made out of particles. They're saying the particles are the ones that are vibrating. Okay, and the question is, if a particle is vibrating, what pulls it up and down or sideways? Okay, something has to take it east-west or north-south. Otherwise, why would the particle return back down again? Okay, so neither particles nor waves can tell you what light is. Okay. The other problem is that this is a transverse wave, and it turns out that transverse waves are the slowest type of waves imaginable. Here you have an example: longitudinal waves. Some like sound, for example, that's a longitudinal wave. It moves back and forth, whereas the transverse wave moves up and down perpendicular to the direction of travel. And so we have a problem here because if you look at the seismic waves during an earthquake, the longitudinal waves, the seismic waves, right, travel 1.7 times faster than transverse S waves, okay, the shear waves. And so we have a problem here because if light were a transverse wave, then longitudinal waves such as sound would travel faster than light. You would, hear the thunder before you see the light of the flash of the, of the lightning. And so we have a problem here because what these people are saying is that, in other words, they've chosen the slowest wave possible, imaginable, to simulate light. And that's where the problem is. Okay, so we have all these problems with the transverse wave. Here it is again. Let me put it back up here. Okay. And so we have all these problems with it. First, it's a bunch of vectors. Those are concepts. They're mathematical concepts. Field is a concept as well. Mathematical concept, just a bunch of numbers. Okay. And travels one way. But what's traveling is not an object. It's not a thing. What you're staring at is an abstract mathematical concept, which they set in motion. Very scary stuff. Okay. And so what do we replace that with? Well, we're going to put something else. We're going to say it's something that looks very much like it, but it's a rope. You can see they both have the same undulation or structural undulation, right? In other words, both a rope and a transverse wave, they really look quite a bit alike. If you were like to, look at them casually, you would say, hey, it looks like the same thing. And you can see why, the electric field runs perpendicular to the magnetic field, because one is perpendicular to the other in a rope. Okay? But the rope is a little different in many respects. One of them is that it's made out of an electric thread and a magnetic thread. And again, magnetic and electric, just to keep with convention, those names, right? It's threads, two threads that are twined around each other, instead of fields that are wound up around each other, or whatever mathematicians propose. So we're talking about a thread. Thread is an object, field is a concept. So these are two different things. We're not just naming things. We're saying that the field of mathematics is a bunch of vectors, which are all mathematical concepts. You cannot say that a concept moves, or that can serve as a mediator for light. On the other hand, thread is a physical object. If you don't believe me, ask your grandmother for her sewing thread, and you'll find out what a thread is. Okay? It's a little string, a little wire, whatever you want to call it, an elongated entity. Okay? And so, we have this proposal there. Okay? And what's the issue? The issue is that this rope, as we call it, these two twined threads, they torque. And a torsion wave is the fastest type of wave imaginable. In fact, it's the fastest thing known to man. Let me repeat that, because maybe it didn't sink in. The fastest thing you can imagine is a torsion wave. There's nothing faster than that. Not a rocket, not not a ship, not a car. I don't care what you put in there. There's nothing faster than a torsion wave. What is a torsion wave? And again, we use the word wave. You know what it is really an in situ torsion of the rope. That's why it's so fast, because it doesn't go anywhere. It just torques in place, and what moves, or what propagates, you could say, along the rope is this motion, this signal, right? You could call it. Nothing is really propagating. What's happening is at the ends of the rope, it's thumping against the two atoms on opposite ends. Because one of the things about this rope is that it's bidirectional. Okay? The rope travels, you could say travel, even though the word travel is incorrect. The rope goes nowhere. But what happens by torquing, it thumps against the two atoms that are at opposite ends. And that's what we call light. This torsion that gives a little push, you could say, a little torsion right at the edge of the atom, at the edge of what we call the electron shell. In fact, the rope makes up the atom itself. And so it's giving this thump to the atom, and the atom is on the same time, it's vibrating and sending signals through this rope as well. It's torquing it. The vibration of the atoms is torquing the rope. And so now we can see why this is a better mediator, or proponent as a mediator for light. Because first, it's a physical entity. It's bidirectional. It goes from the atom in your eye to my eye, and vice versa. And also simultaneously, okay? And it's torsion, which is a faster wave than either transverse or the longitudinal wave. And it's fast because it goes nowhere. Okay, that's essentially the summary for that. But here you see it. Why? Einstein, among others, believed or came to the conclusion, right, that light travels always at a constant speed. There you have the speed of light, little c, which is 300,000 kilometers per second. And what is it equal to? It's equal to frequency times wavelength. That's what the little f and the lambda there stand for. Frequency and wavelength. Meaning, if you raise the frequency, you must lower the wavelength for little c to be constant, and vice versa. You raise the wavelength, the frequency must drop. And the only entity in the universe, the only entity imaginable that can simulate this is a rope. Okay, as you can see on the right, if you torque a rope more and more, you will get more links, and each link will be shorter. And if you untorque it, well, you get the reverse. You get the links are longer, and you'll have fewer links for any given length of rope. So we do have an explanation, not only for the speed of light, we have an explanation for why it's bidirectional instead of one way, like the transverse wave or the photons of quantum mechanics. We have the right shape. It's an undulatory shape. It's a structural issue there. Okay. What else can we look at? You also have one thing I haven't touched upon is the amplitude. Okay, so you do have amplitude in the wave. It's got all these features that a wave is supposed that light is supposed to have. And so yeah, this is what we essentially simulate light with. Here you have the dynamic version of that. Okay, that's more or less what we're proposing. We're saying that whereas the wave, the transverse wave, travels in a single direction, and it has all these vectors, which are mathematical concepts, these fields, which are mathematical concepts. We're just talking about magnitudes, values, units. That's all we're talking about there. And you compare it against the rope, which not only explains the speed of light, but it has the right structure, and it's bidirectional. Okay, and so we think it's a much better candidate for light than what we have today. And I'm talking about both the transverse wave as well as the photons, a series of little particles, which is actually what they really simulate it with. If you go to the standard model of quantum mechanics, you won't find any waves. What you will find is the photon. What is a photon? A particle. It's called particle, the standard model of particles. Quantum mechanics is a particle theory, corpuscle, you know, but it's not a corpuscle because, again, they say that the particle is not a particle. Particle is a number. That's what they accelerate at the CERN and SLAC and Fermilab. All these people accelerate numbers, okay, values. When they talk about energy, they're not talking about a little gas or anything like that. They're talking about particles, okay? I'm sorry, they're talking about number of particles, yeah, but the particle is the number. Okay? It's just the value that they have, and they play around with the values. That's how they can transform energy into mass, mass into energy. They play around with charge, and all these words are mathematical words, and all they have to do with are values, magnitudes, amounts. That's it. That's all they can put in an equation. They cannot put the word rope in an equation. They cannot even put the word wave or the word photon in there. Okay? No, they have to put a number, the value. So keep that in mind when you make up your own mind on whether, you know, what could be the mediator of light. And yes, there had better be a mediator of light, because during the photoelectric effect, what you have is, this is at least the interpretation, right? That you have a photon, little ball, that hits the electron ball, right? And compels it to move to another atom, and the flow of all these electrons from atom to atom, that's what electricity is. And that's what a photoelectric effect is. You have a beam of light shining on polished metal, and a current flows. And what's that current? A bunch of electrons moving from atom to atom. What triggered it? The photons that hit it. Okay? And so they have a series of particles hitting a bunch of particles known as electrons, which start to move. Okay? So the photon had better be something if it can move an electron, which is alleged to be a part of our 3D world. Okay? So that's the story. Okay, moving on here. I'm going to start today with a little recap, okay, of what I did the other day, which is the black hole singularity, especially. Okay, what is this singularity thing? It's we found out it's a little bit scary stuff. That's what it is. Okay, so this is what I showed the other day. Give me a second here. Let me put it in motion. There it is. It's this is the astronaut falling into a black hole, and he gets stretched all the way to the singularity. Okay, and this is what they illustrate. And yeah, this is what they say is happening with anything that falls into a black hole. Once it crosses the event horizon, it gets stretched all the way to the singularity. And that's kind of weird because, not only because it's weird in itself, but it's weird because the majority of mathematicians out there say something totally different. They say that as soon as you pass the event horizon, you get crushed out of existence at the singularity. You go zip into the singularity and get crushed out of existence. Every atom in your body gets crushed out of existence. It gets turned into empty space. No size, no shape, no nothing. Okay? That's the official version. And here it is. Don't believe me. Here are the experts. Okay? Has one fellow there, Cole Miller, University of Maryland, crushed out of existence. And you see others there. They say exactly the same thing. All atoms, every piece of matter is crushed out of existence. Okay? So that's, I would say that's the majority view, or that's the off the cuff, statement that they'll give you. They say everything gets crushed out of existence in a black hole because it goes through the event horizon immediately at the speed of light, obviously, gets sucked into the singularity and gets crushed out of existence. Its shape, everything goes away. Okay, so that's their version, but here you have another fellow I talked about the other day. His name is Derek Miller, and he says the following: he and his rocket ship do not disappear. Talking about an astronaut, right? Penetrating the event horizon. Instead, they seem to stop frozen in time. So once you cross the event horizon, you do not disappear or fall instantly into the singularity. No, you get frozen in time. You're suspended in time, so to speak. And he says, but if you could see that light, you would see everything that has ever fallen into the black hole, frozen on its horizon, including the star that formed it. Okay, so he's saying what? He's saying that all objects that fall in through the event horizon are still there. Okay, the only problem is you can't see them. It's a question of observer on the outside not being able to see what's inside. But they have not disappeared. They have not been crushed out of existence, according to this fellow, this expert. Okay, so we have a little difference of opinion. Looks like the math leads to different conclusions. These fellows say, hey, the mass is so great, the gravity is so great, it's going to crush any bit of matter out of existence. This fellow says, no, you're suspended in time. It's just the outside viewer, the observer, he cannot see you because you're not emitting light. The object that fell is not emitting light towards the observer, far away, distant observer. That's the issue, okay? So we have a difference there. Either it gets crushed out of existence or it's still there, you just can't see it. Those are two different things, okay? And in fact, Derek goes further and he says, you could find yourself in a white hole, which would push you out into a whole other universe. That little point there where they cross singularity, that is an Einstein-Rosen bridge, right? And then what it is just a little line. They say a one-dimensional line that connects these two universes, okay? It's a bridge that is long. It connects the space of both universes. If you go beyond it, you end up in the parallel universe. So that is how we could use a black hole to travel from one universe to another. Okay, we have a little bit of a problem here as well, because what this fellow is saying is that not only you get stretched, from event horizon all the way to singularity. I mean, you can imagine a poor astronaut, he gets stretch, and somehow he survives that stretching, goes right through the zero-dimensional singularity, through the one-dimensional Rosen bridge, and come out of another universe. So the astronaut doesn't die. He says there's a possibility he survives and goes to another universe. Now that is weird, because now I'd like to stretch you on the rack. Forget about being stretched from the event horizon all the way to singularity. I'll stretch you on the rack, and once the doctors fix you up a little, see if you can travel anywhere. But he says you survived the trip. And in fact, here you have one boson. He's a boson. And his name is Brian Greene, and he travels through a wormhole, and he goes to see himself, I guess in another universe. But he says he goes to see himself in the morning. So that's him traveling late at night and finds himself with his own self in the morning. Okay, so I guess you can travel to another universe or stay here on Earth. You'll just be, traveling to see yourself early in the morning. And this is what these people put out there as science. Right? This is science. It's really quite scary when science gets like this, because if they show me and they say this is a cartoon or this is just to have fun or laugh a little, no problem. But when they put this out as science and they say this has been proven mathematically, well, then we have a little bit of a problem with that. Okay, and here's a lady I showed her last week. Okay, and let's see if I can get this up here. And her name is Jana, and John 11, and this is what she's going to be doing. She's going to tell us something about the singularity.
A black hole might be different than you imagine. It's a place and not a thing. The core of the star keeps collapsing, and where it goes, nobody knows. The black hole isn't anymore a crush of matter. It left it behind in its wake, but the stuff of the star is gone.
Okay, so she says that any matter that falls into the black hole does absolutely get crushed out of existence at the singularity. Nothing is left behind. So we have these contradictions between these people. Either you get stretched, either you stay on the surface of the event horizon, near the surface, or you fall into the singularity and you get crushed out of existence. Or I guess the fourth one is that you're stretched, and despite being stretched and all your bones get broken and all your muscles get pulled out of alignment, you are able to go through the singularity and end up in another universe, or early in the morning when you were drinking coffee. So you tell me which one of these scientists is correct. I mean, we have contradictions here, right? And but then Jana says not only that it's singularity is a place and not a thing, then she corrects herself. And here, I want you to hear her correct herself. See what she says. She says it's not a place, it's something else.
Once you pass the event horizon, space becomes time and time becomes space.
So from the outside, if you're an astronaut, you're watching your friend, another astronaut, going into the black hole, it's as though your times become rotated relative to each other. So the profound thing is, as an astronaut on the outside, looking at this round event horizon, you think of the center of black hole as a point in space. But to the person who's fallen in, it's not a point in space at all. It's a point in time. The singularity, or the end of it all, the crush in the center of the black hole, is in their future. So they can no more avoid the singularity than you can avoid the next instant of time coming. So the death in the singularity is inevitable, although we don't really think the singularity necessarily exists.
Although we don't really think the singularity necessarily exists. Although we don't really think the singularity necessarily exists.
That singularity probably doesn't ever actually form.
That singularity probably doesn't ever actually form. That singularity probably doesn't ever actually form.
So the singularity never forms. It's not a thing. It's a place, but actually not a place. It's a moment in time. What are we talking about here? I mean, we went from an object, a thing that's going to move stars around out there somewhere, and it's not a thing, it's a place. Now she says it's not really a place, it's a point in time. You tell me what we're talking about at this point. I mean, they keep changing the goalposts here, switching it, pushing it forward or backwards or whatever. And here we have another bozo, and boson. And his name is Derek Miller, and he's going to tell us the same thing, more or less, that it's a moment in time.
Since the future always points up, it tells us that the singularity is not actually a place in space. Instead, it's a moment in time.
The singularity is a moment in time. The singularity is a moment in time. The singularity is a moment in time.
The very last moment in time for anything that enters a black hole.
Okay, so it's a moment in time according to these experts. Okay, yeah, some say it gets crushed out of existence. Others say the matter remains there. Now he says it's a moment in time. What are these people talking about? Why are they giving you physical interpretations if later on they're going to say, well, we don't do that in physics, in mathematical physics. We don't give physical interpretations. Then why are they trying so hard to give you a physical interpretation? I mean, they should stick to math, right? I mean, you would think. And here he's going to confirm to us that, yeah, it's everything that's fallen in there stays at the surface, I guess, of the event horizon. In theory, you would see everything that has fallen into the black hole frozen on its horizon, including the star net forming. But in practice, photons are emitted at discrete intervals, so there will be a last photon emitted outside the horizon. He's only telling you what you can see, not what is real, what exists. And therefore, these images will fade after some time. And he said, this is the video about real science of black holes. Okay, so he's going to talk about he's going to give you a lecture, a real science lecture on black holes. And he says that all this stuff is suspended on the event horizon. It's timeless. It stays there forever. It doesn't get crushed out of existence, I guess. So I don't know, you tell me. What conclusions can we reach from all this? Well, here's a summary. Okay, we have most math experts have calculated that singularity crushes all matter out of existence. Not one atom survives. But expert Janet Levin confirms that all matter is gone. There's no matter there. Okay. I guess she's in line with all these people. But then she changes her mind because she's going to give a different idea later on. He says, all gone, but, and here you have other mathematicians. They tell you that matter stretched forever from the event horizon to the singularity. Okay, so now if it's gone, how come it's stretched? What's being stretched and for how long? And it says stretched forever because, the astronaut's feet, which went first through the event horizon, never reach the singularity because it's always in the future. The singularity is never in the present, it's always in the future, she says. Okay, so here these people have their feet close to the singularity but never touching it because it just goes, it's always in the future, in their future. What the Derek Miller says, he argues that objects never reach the singularity. There you go. And Jana says that a singularity is a place. Okay? Then she corrects herself and says, no, she says it's actually a moment in time. So is it a place or a moment in time? And Derek Miller confirms that a singularity is not a place, but rather a moment in time. So the question, are these mathematicians kidding us? Are they experts? What are they doing? Are they just entertainers, clowns, giving these so-called scientific presentations? And then the bottom line question, the ultimate question, why are they giving physical interpretations, right? Why are they giving you all these physical interpretations if mathematicians, mathematical physics, they're on record that stating that math physics is solely about equations, okay? So if they're going to do equations, why don't they stick to equations? Why are they giving you a physical interpretations if they don't do physical interpretations? And the only physical interpretations they have are irrational. Why are they harping on it? Why are they including it in their dissertations? They should keep that out. Because they're giving you an irrational interpretation. They tell you to believe it. When you confront them, they say, well, we don't do that anyways. That's philosophy. So this is the status of so-called science today. And so you got to keep in mind the context here, how these people are handling the propaganda. They're commercial for mathematical physics. And that's what they do. They're just proselytizing stuff that ain't so. Okay, so let's move on to the subject matter of today. And I think that'll serve as an introduction to what we have today. Here we have this lady, and her name was Alice in Wonderland, a book written in the 19th century. Okay, and she falls into this black hole. Okay, falls forever and ever and ever and ever. I guess she does reach a bottom, but this is more or less the bottomless pit that the mathematicians are talking about when you fall into a black hole. One of their so-called black holes, okay, says you fall into this thing forever. You never reach the bottom, okay? And fortunately for Alice, she doesn't get stretched out of existence, or completely to a little thread. She falls in one piece, apparently, okay? So she was lucky. Okay, so lots of people fall into rabbit holes, and they end up, talking to rabbits and, thinking nonsense stuff. Here's one guy, his name the Mad Hatter, and with his rabbit talking to Alice. And these people end up like her, more or less like her, talking to these weird characters, and they believe that these characters are real. But actually, you should change the name. He's not a Mad Hatter, he's a Mad Hater. Okay, he's a mad hater. Some of these people then hate you, and they hate you for, challenging their beliefs, their ridiculous beliefs, and they don't like that too much. And I had two fellas come over, and they threw a little rotten tomatoes in my face. One of them says the following. He says, if you want to prove something, learn math. Yeah, I guess if you prove, in math, they do proofs in math. We don't do that in physics. That's in religion of math, but when they prove things, okay? And they're really tautologies. They're not, proofs in math are just tautologies. Whatever's on the one side of the equal sign is equal to whatever's on the other side of the equal sign. That's kind of, redundant. It's a tautology. You're just stuttering. That's all you're doing. And so most scientific theories are then proven with math. Now, theories are not proven, first of all, and they're not proven with math because theory is an explanation, and math cannot explain. Math can only describe. It has no power whatsoever to explain. When you see an equation, it's not an explanation, it's a description, a mathematical description. And another fellow comes over and he says the following. He says, it's clear you don't understand physics or the scientific method, okay? Slap in the face, okay? Science is not about technologies. That is the province of engineering and applied physics. And no, he's absolutely right. Science is not about technologies. But he shouldn't tell that to me, I know that. But he should tell that to all the mathematical physicists on planet Earth, because they're all investigating stuff related to technology, and they call it physics. They're trying to develop these supercomputers or, all kinds of devices that they go out there and invent or try to invent. And what happens? They're trying to make money, seeing if they can patent something. And what they're doing really is developing gadgets. And they don't know how a field works or how gravity works, and they don't care about any of that. What they're doing is doing technology. And that's one issue. The other issue is that, a lot of the Nobel Prizes in physics, quotation there, are given for inventions. And you can look that up, and you'll find out that many of them, I'd say at least 50% of them, have been given for inventions, if not more. So they don't give physics prizes for science, for explanations, for physical interpretation. They give physics prizes for developing technology. So you're talking to the wrong fellow. You should be talking to all these other mathematicians about that, because they don't seem to understand it. But then he continues, he says, in physics, that requires math models. No, absolutely not. If you're going to explain, like he says there, you must explain. If you're going to explain, you can't use math. Math has no power to explain again. It can only describe. That's the problem with math. It's very limited in what it can do. And then he said, provide predictions. No, we don't do predictions either. Again, that's a mathematical thing. If you know you're traveling in a straight line, your car is traveling in a straight line, 50 miles per hour, constant speed, you know you're going to be, you can predict, right? Predict that you're going to be 50 miles away from your starting point after 1 hour. Okay, that's a prediction. But that has nothing to do with an explanation. You haven't explained anything. All you said, hey, I can predict that you're going to be over here. A prediction is nothing more than a description. That's why mathematics has said that that science is about mathematics, because they can predict, they can measure, but what they cannot do is explain. Okay, and that's why they convert science into descriptions. Okay, and that's what we have today, just descriptions. The explanation part, which is what all these people really do, is always irrational, especially for all the invisible, intangible phenomena, or phenomena mediated by invisible, intangible entities. Okay, they have no explanation for that whatsoever, because they don't do objects, they don't do things. What they do is equations. Okay, and he gives some examples there, black holes among them, and instead of pseudoscience, crackpot claims all those actual facts are false. No, we don't claim that they're false. We claim they're irrational. The explanation is irrational. We say there's some phenomenon out there, obviously, and has a different explanation than the one provided by mathematical physics. So we have to put it in the right context. Okay, and these people try to take it out, and they're raising scarecrows here, saying that we're saying that they're wrong or they're false. We don't use those words. There's nothing wrong or false in science. Okay, you either have a rational explanation or you have an irrational one. And if it's irrational, it doesn't belong to science. That's where all of mathematical physics belongs, especially with regard to invisible, intangible mediators. Okay, so where does all this stuff come from? Where do these people get all these ideas? Well, they get them from the monastery. And here you have a series of people out there who make money, you know, on the internet and on television, etc., where they spread the good news of mathematical physics. And you'll probably recognize some of these folks. Here they are, okay? Let me show you. Here goes. You have Bill Nye and Jim Al-Khalili, two fellows who are out there proselytizing, you know. Here's some more, Sabine Hassenfelder and Brian Cox. All these people talk about all the nonsense of mathematical physics, and what they're giving you is explanations. They're giving you physical interpretations, all of which are irrational. Not one of the things that comes out of their mouth are rational, okay? And so these are the heroes of today, and these are the people these people listen to, and the ones who they follow and whom they believe in, okay? And this is where the problem stems from, you know? So just keep in mind, this is where it all begins, okay? These people are the ones that brainwash the masses, and this is who the people believe in, because they see them every day on television, or almost every day, I'd say, and they think these are scientists. They think these are physicists, and they're not. They're just a bunch of mathematicians with the most irrational explanations they can offer for phenomena such as gravity, magnetism, light, workings of the atom, galaxies, etc. All of them are irrational explanations. Not one survives today. Not one survives science. Okay, here we have one famous, or somewhat famous, he's a lesser individual, but he's quite known out there, and he tells us that he's got a group of scientists who help him do his YouTube videos. And this is what he says. He says, I have physicists on my team who help with the research as well as make sure the information I present is accurate. When we produce videos outside my or my team's expertise, we consult appropriate experts to make sure our information is as accurate as possible. Good. No scientific theory can ever be proven. It can only be falsified. Well, we agree with the proven part. How about this notion that it can be falsified? Well, I don't know about that. So he says, so anytime someone asks where's the proof, I know I'm dealing with a non-scientist. Yeah, what good old Arvin failed to realize is that falsification is proof. Okay, here it is. We kind of pointed out to them, when you say that you falsified something, all you're saying is that you convinced someone that something is false. In other words, you proven to him. You made him believe. You made him change his mind, and instead of thinking that it's truth, it's false. So falsification is a proof. And this is one of the people out there making money, trying to sell, the nonsense of mathematical physics. So, he already starts out on the wrong foot. That's what he has in his website. And you wonder about these people, because these are the people who are going to give their presentations, and people are going to listen and follow and say, oh, this guy's an intelligent guy. He knows what he's saying. No, he doesn't. If he talks about falsification and doesn't know that that's proof, same thing as proof, it's a synonym of proof, I don't know what to tell you. Means what did this guy learn in his life? Okay? Or while he was at the monastery, the mathematical monastery. And here we have another fellow, and a lot of you know him. His name is Sean Carroll, and he's going to tell us something, again, about fields in this case. And he's saying that particles are actually fields. Okay, here it goes.
Think about a magnet. A magnet is something you can attach to a piece of metal, right? It'll stick to it, a refrigerator or so forth. You can stick lots of things to lots of other things. You can stick pieces of tape or gum or whatever. But when you stick a piece of tape to the refrigerator, the tape has to touch the refrigerator in order to stick. The gum has to touch the refrigerator in order to stick. A little insect or gecko walking up the wall needs to touch the thing in order to stick to it. A magnet, if you hold it close to a piece of metal, you can feel it pulling before it touches. The magnet reaches across empty space and exerts a force, and the refrigerator exerts a force back, according to Sir Isaac Newton, that pulls the two things together. They don't need to touch each other. How is that possible? How does the magnet know that there is a refrigerator nearby that it should be attracted to? Sir Isaac Newton was very puzzled by this phenomenon, which is known as action at a distance. Newton was interested in gravity, not magnetism, but it's the same thing. The Earth exerts a force on the moon, or satellites orbiting the Earth. They're not touching each other. The Earth seems to push out across empty space to exert this force on things in its vicinity. Newton said that you can understand gravity throughout the universe in terms of an inverse square law. The force of gravity becomes weaker and weaker as you move away, as the distance between the two objects squared. So, but he was very worried. In fact, he said that this phenomenon of action at a distance made no sense.
Okay, so what we have here is all these people talking about action at a distance, and they're saying all these fields are actually particles, and particles are fields. And so what are we talking about? Are we talking about something that's concentrated at a point, meaning a particle, or are we talking about fields that extend forever, and which they say vibrate locally, and that's going to be called a particle? That's kind of like cheating. That's what it is. They're saying we're going to have the best of both worlds. We're going to have a localized thing as well as something that's extending all the way to the edge of the universe. And that is, you can't have both, but that's what they say that a field is. Oh. That guy went out of focus there. Okay, I think I'm back. Okay, let me know if you see me still there. Okay, so what does this Arvin guy have to say about that? Well, this is what he says, that fields are teeming with virtual particles that pop in from nowhere and then go back to being part of the field. And so, they cheat. They say that at the same time that the local vibration of the field is a particle, at the same time they say that these things pop in and out of the field, out of space, I guess, because space is a field or covered with fields or completely filled with fields. So these people, all they do with their physical interpretations are cheating. And so this other fellow who said, that you're supposed to explain Well, yeah, when you introduce magic, you can explain anything. These people are introducing ghosts and goblins. These people who listen to them, they think that the so-called scientists, the so-called physicists, that they're giving them a scientific presentation when what they're doing is not even fantasy, it's just totally irrationality. Can't even be imagined what these people are saying. Here's another fellow, and he talks about strings and gives you again the subject matter that these people talk about to the public. And some people believe them because they're just believing them on the basis of authority. They're saying, oh, he knows so much, he knows all that math. Yeah, but the explanation he's giving them is a bunch of bunk. And here you see Brian Greene. Listen to him. He's going to talk to us about strings. He's going to tell us what a string is made out of.
What is the orange made of? Molecules. And if I make them big enough deep inside, I begin to see atoms. We have electrons, mostly empty space in the atom, but deep inside, we see the nucleus. That the nucleus is itself made of particles, neutrons. I magnify it, I find little tiny quarks inside. And I magnify it, string theory says I'll find a little filament of energy, a little string-like filament. So a quark is nothing but a string vibrating in one pattern. An electron is nothing but a string vibrating in a different pattern. A neutrino, nothing but a string vibrating in a different pattern still. So if I take all of this back together, I have my ordinary orange. Deep inside the orange or any other piece of matter is nothing but a dancing, vibrating cosmic symphony of strings.
Now, isn't that a magic show? Was that all about magic? Everything is made out of strings. In fact, what's so weird here, you have the atom is a string, okay? And the proton is a string, a neutron is a string, the quarks and gluons that make them up also are strings. So they're all strings, but so you have all these nested strings, okay, vibrations of strings. And so what sense does that make? What does that bias? What does that tell us about the universe? Okay, and then of course, the strings, as you can see, they're all closed loop. And so they're separated from other strings, meaning that you have a discrete particle here and a discrete particle there, okay? And the question is, does that make any sense that you have these vibrating strings and that's what an atom is? And assuming it were correct, if that's the case, so what? So what can you tell me about gravity? Why does a pen fall to the floor? Why does a magnet attract another? And they cannot answer those questions, and they're talking about things that they invent, that the particles are made of strings, closed loop strings. Okay, but here we have Leo Susskind, another fellow, and he's going to tell us what the string itself is made of. If everything is made out of strings, what are the strings made out of? I think a lot of people want to ask that question, and it's interesting to hear his answer. Okay, so here goes. Here goes.
Is there any either evidence or reason to believe that, in some sense, strings are the most fundamental things? Could strings be made of other things? In the march of reductionism, is there some sense in which strings are the most fundamental things in the world and there's nothing smaller than them, or they're not made of anything? And I gave an answer which was the ultimate hedge, or the ultimate waffle, and that was, we have learned that that's not a good question. The question of whether something is composite or fundamental should really be asked in the following way. You should ask, is it useful to think of it one way or the other, and whether it's useful or not may depend on the values of the parameters in the theory. So there's no invariant ultimate answer to the question, which is more fundamental. It's a question of which is useful. Fundamental means it can't decay, and composite means it can decay, it can break up, it can fall apart. Are strings fundamental? There is one set of parameters in the theory where strings are made up out of little things called d-branes. You change the parameters and you find that d-branes are made up out of the strings. So it's a question of useful. There are ranges of the parameters of a theory where it's useful to think of the strings as the most fundamental objects. You can shift the parameters and find ranges of parameters where the things that are called d-branes, which previously had been thought of as big fat composite objects, morph into tiny things, and the strings themselves blow up into big fat composites. This is a lesson that I think physics has been driving at for some time. The sort of continuous march of reductionism. Smaller things made of smaller things made of smaller things, and some ultimate sense of what the most fundamental thing is. That does not seem to be the way things are going. The way things are going is that things morph into each other when you change the parameters in the theory, and what was fundamental can become composite, what was composite can become fundamental. What the ultimate lesson to learn there, nobody knows.
So now you know, strings are made of d-branes, and d-branes are made of strings, on and on and on. And where it leads mathematical physics, nobody knows. So that's the state of science today, instead of physics. Okay, and finally we have another fellow here, another example to show that all these people talk nonsense. His name is Matt O'Dowd. He has Space-Time on PBS. And this is what he has to say. Listen to his version. Here it goes. The Higgs boson, by the way. Here it goes.
Now take the photon. It is definitely massless. It travels at the speed of light, and it experiences its entire existence in an instant. A photon only changes if it bumps into something else. But the photon and the electron are both just excitations in their own fields. So why does the electron have mass and the photon not? While the photon can cross the entire observable universe without bumping into a single thing, the electron is never not bumping into things. There's something in the substrate of space everywhere that impedes the electron. It's the Higgs field. The Higgs field is really weird. The Higgs field has a positive strength at all points in the universe. There's a little bit of Higgsiness everywhere. This makes the Higgs field an infinite source and sink of weak hypercharge. On its own, the electron would travel at light speed, but trapped in this Higgs field buzz, the electron feels mass. Honestly, this is a pretty wild story. An invisible and infinite ocean of some sort of charge that we've never heard of, all invented so that electrons can be left and right-handed at the same time. How do we know it's true? Well, something like this must be true, because all of the rest of quantum field theory hangs together too well. We conclude that QFT is essentially correct, but it's an incomplete theory without a mass-giving field. The Higgs field is the best, least silly option to do this. But how do we prove it? Enter the Higgs boson. Just like the other fields, the Higgs field can vibrate around its baseline value, which gives us the boson. This particle actually has nothing to do with giving anything mass. However, if we observe the particle, then it means that the field also exists. It seems very likely that the LHC did produce the Higgs boson, which in turn would mean that the field exists. Could the Higgs field also explain things like dark energy, inflation? There are reasons to think it might.
Yeah, all theorists believe that they can explain everything with the Higgs boson. And yeah, this fellow is a caricature of a scientist, of a physicist. He has no idea what physics is about. And what they do is they go around in circles. They'll never give you a rational physical interpretation. And later on, they dismiss it as philosophy. Why are they giving you a physical interpretation if they say, first of all, that it's not part of their line of work, their job description? That's on the one hand. And then the other, if they only do math, why do they even take the trouble, right? And then they give you an irrational one anyway, so why did they even take the trouble? That's a question you should be asking. And that's not the worst part of it. All these so-called scientists, that are on the internet and on television, they had to branch out into other disciplines, and they become experts in other topics. They're not, or maybe their bucket of physics is completely full. They've already talked about everything they could, and so they have to branch out into other, line items. And so they start talking about other stuff where they give their opinions as experts. Again, they're always experts, right? And let me show you some examples here. Here's a lady known by Sabine Hossenfelder, and she talks about nuclear waste and about climate change. Okay, is she an expert on that? Why is she being called to do that? I thought she was a physicist. Okay, she's giving you her opinion on these subjects. She also talks about electric cars and whether women athletes, should be competing against, the people who change their sex, against men who change their sex to women. Here you have another fellow. His name is Roger Penrose, and what does he talk about? He talks about consciousness and whether a creator exists. Okay. He's supposed to be a physicist, right? This is what they're talking about. They're going into stuff that you would think involves philosophy, psychiatrists, or psychologists. And these people are giving you their expert opinion on that. Why are they being called to give expert opinions on subjects that are not part of their discipline? And here's another one. His name is Nick Lucid, and he talks about autism, okay, and other subjects like, in this case, whether you should work or whether you should be working so hard, for a living, I guess. Take it easy, he's saying, right? They're giving you their opinions, and a lot of people might believe them because they say, oh, these are experts. They're on TV, they're my heroes, whatever. Here's another one, Michio Kaku. He talks about brain size comparison, okay? Talking about the complexities of the brain. Is he going to become a surgeon, a brain surgeon? Why is he talking about subject matter why is he being called to talk about these subjects? Or he talks about Hawking's opinion on God, Again, religion, are they experts in religion or what? Why are they being called upon to talk about these subjects? Here's Bill Nye. He talks again also about religion, creationism, and whether we should teach that to children, like the monkey trial, a long time ago. And he talks about nuclear power, Monsanto, and other stuff, changing your mind. Why are these people being called to talk about these subjects? Shouldn't they be called to talk about physics? Is it that they have their plate already saturated, all the physics subjects saturated, and now they need to talk about something else as if they were experts because they're being brought in as experts? Here's another fellow. His name is Neil Tyson, and he Neil deGrasse Tyson, right? And he talks about gender, and someone accused him also of putting his hands where they don't belong. And he went to Barbie Land in Florida. Great. This is subject matter of physics. Why is he being called to talk about these petty subjects? Is he some kind of expert? Why are they calling him for all this stuff? Or are they bringing him on the basis of, again, authority? Like he's a known figure, so to bring in the hits, they bring him in to talk about anything that has nothing to do with physics. Okay. Here's another fellow. His name is Brian Greene. What does he talk about? He talks about consciousness and psychedelic. Whether you should be popping pills in your mouth, I guess, or shooting up. Great subjects. I don't know if he's an expert on that. Has he shot up, or is that why he's bringing these subjects up? And here's another Brian. His name is Brian Cox, and let me get him up here. And he's talking about aliens and what it means to be human. And how would he know? How would he know what it means to be human? I don't know. These people come in there with their opinions. Are they worth anything, their opinions, or are they worth as much as the next guy over? Why do they bring these so-called physicists? Are they supposed to give you a better opinion than the next guy down? Okay, so I guess they're making money by branching off into these other subjects, right? Okay, so what do you see in the publications today? What are people publishing out there? And here you see they publish these images, right? This is supposed to be a black hole. This is what they feed the public, and comes from all these people. Also, they will put it on their websites and on their YouTube videos, and that's what they show you. You say, okay, that looks fantastic, right? But it turns out that's just a drawing, an image that someone made, or a computer-made image. This is what they actually see in the night sky. And from this, they conclude, they infer that, that you have these black holes. I mean, can you tell by looking at this that you're staring at a black hole? And what they do, they look at what's happening to the mass or the, I guess, the suns and the gases in the region. They say, oh, it's moving so fast, there must be so much mass that's causing it. And what else could it be if not a black hole, which is all mass and no matter? Okay, that's more or less the situation. That's how they prove all these things, and they feed this to the public. Here you have it in the other world, in the quantum world, and this is what they show you. And you see these so-called traces down at the lower left and the upper right. And you see the atom there, this is the typical atom, a bunch of little balls in the center. And I guess they're orbited by all these other particles that are supposed to be electrons. Is this a picture that they took somewhere in a lab, somewhere with high-powered microscopes? No, this is what they see with their high-powered microscopes. And there you do not see any little electron beads flying around. What you see is a ball, or something that looks like a ball in 2D, the 2D version of a ball. Okay, you can see there on the upper right, sticking up from the metal there, IBM it says, by the way. And you can see that the atoms have kind of like structure. You don't see a little bead going around the proton. Okay, so one thing is what they illustrate. They constantly illustrate a lot of stuff, and what they actually see is stuff like this. So you wonder how much are you being cheated by all these false representations of so-called physicists, and the images that they show you, they're not real. 99% of the stuff that you see out there today is not real. It's because they can't see it. It's not real simply because they can't see it. They have to make a drawing of what they think it is. And the drawing shows, if it shows a bead with a electron bead moving around it, around the proton center, then you have to ask the valid question. Why does the bead fly away? What keeps it tied to the proton, to the nucleus? And these are questions you'll never have an answer to. Okay? I mean, one is negative, one is positive. The negative should fall and be attracted by the positive and stick to the center. And opposite of that, why doesn't it just fly away? And they can't tell you that. But that's what they illustrate, but that's not what they see. And they talk about observation. Okay, so here we have good old Alice falling down a black hole, I think. Rabbit hole, I thought it was originally, but today I guess she's falling down a black hole. And she goes down forever. She'll fall all the way until she hits nothing. She will just fall forever. And you can picture her again stretched completely if she falls into a black hole, so that she's like a little rubber band being stretched, okay, from the event horizon to the singularity. Okay, that's one way of looking at her. But yeah, this is how these mathematicians have been falling for the last 400 years. They've been falling and falling into black holes because they're actually painted themselves into a corner. They think they can figure out how this universe works by looking at the math, by looking at equations, meaning descriptions. And what people are asking or expecting from them are explanations. Since they cannot give you an explanation, what they give you is the next best thing for them, which is irrationalities. They say, look, we think this is the answer to your question, and the answer is totally irrational, And when you put them against the wall, they say, well, by the way, we don't care about that because what we do is math. So why did you attempt to tell me that you're an expert in physics, in physical interpretations, if all your explanations are irrational? That's the question that you have to pose to them. So, so we're back to our tea party, okay? And here we have these people who have fallen into a black hole, and they're, with Alice there, I guess, Sabine, and they're all, just talking nonsense for the last 100 years. And these are the disciples. This is where we ended up, with all these people giving you irrational explanations for everything that's been up there. The only guy I would really like to see there is good old Einstein. He was one of the guys who started all this mess about 100 years ago, a little over 100 years ago. And I wish he would have fallen into the black hole, the Alice's rabbit hole, Wonderland world, and maybe got to see the Queen, And according to the tale, it says that the Queen sentenced the Mad Hater, right? Sentenced him to death because she accused him. She says, "You killed the time." And Einstein, I think, did kill the time for sure, okay? And, maybe the Queen should have put him, in a stockade like that and then chopped off his head if she was really going to go through with her idea that, he deserved the death penalty, okay? Anyways, that's the story for you today. And all I can tell you is whatever comes out of mathematical physics, you can't even take with a grain of salt. It's just worthless garbage. It's nonsense, poppycock. We don't have any more science out there. Everything you read in the scientific literature, so-called scientific literature, none of it is science. They're all doing black holes, they're doing dark matter, they're doing dark energy, wormholes, parallel universes, Big Bang. That's on the cosmological side. On the Lilliputian side, you have the atoms and what comes below that, which are all these phenomena / particles, things that they can't see, which they imagine to be particles, and they invent new words for them every day. They mediate all transactions with energy, with force, with waves, with time. These are the mediators, the physical mediators, and they're all their physical interpretations. And so nothing that comes out of science today is rational anymore. And it's very, discouraging. What can you say? This the world we live in. This is the world we ended up with after doing math for 400 years.